Okay, so next speaker, Shira Chapman, talking about the heterolography from quantum information. Please.
Thank you. So, hi everyone. I'm indeed Shira Chapman. I'd like to start by thanking the organizers for giving me the opportunity to speak in this wonderful conference. And today I'm going to tell you about some baby steps that we've been making towards developing a theory of the heterolography. This talk is going to be based on work that we did together with my postdoc, Saskia de Mulder, and my student Osher Shoval, and together with Damian Galante and Sam Sherry from King's College in London. And so this was the title originally assigned to me by the organizers, but a more specific title could be that one. All right. So the question that I would like to answer, like some of you in this room, is what are the microscopic constituents of quantum gravity? And for the case of gravity in ADS, holography was extremely useful to answer this question. In particular, when focusing on low dimensions, we know that ADS2, nearly ADS2 gravity is dual to SYK. And this discovery gave us a very concrete idea of the microscopic constituents. In particular, in these developments, quantum information and chaos played a very important role. And so this raises a very natural question, since we do not live in ADS, whether any of these developments can be carried out to the Cetal space. But before I tell you how to start and make some baby steps towards the Cetal holography, I better tell you why I think that the Cetal should be holographic. And the main point to remember about the Cetal is that observers in an expanding universe are surrounded by a cosmological horizon and don't have access to the full space-time. And this horizon has an entropy associated with it, which is consistent with an area law formula. And so this raises the question of what exactly is this entropy counting? So in the case of ADS, the fact that we have a time-like boundary with a dual theory on it allowed us to make progress in answering this question. But in the Cetal, we do not have a time-like boundary, and so this raises the question of how to proceed. Nevertheless, the fact that we have an area law does suggest that a microscopic description could exist. And so, yeah, so how do we proceed from here? If at the moment I focus on the low-dimensional setup in particular, then we have a hint. And this hint is the fact that in low dimensions it's possible to embed the Cetal space inside ADS. So essentially to form a space-time which has a de Sitter interior with a cosmological horizon and an anti-de Sitter exterior where the dual field theory can live. That's very different from the setup that was discussed in the previous talk where the dual field theory would be living at future infinity. Here it's essentially holography for the static patch. However, there is a problem, is that we do not know, we have no idea what's the field theory dual to this setup. And keep in mind that this is in low dimensions. But we still have an exterior which is ADS, and if we go with the usual holographic paradigm, we could expect that essentially we are making an infrared modification since we are changing the interior of the space-time. So we don't know exactly what the field theory is, but we can carry some gravitational calculations in this background to try and see what we expect if indeed this space-time has a dual. And some of these calculations indeed have been carried out, and in particular, when thinking about chaotic properties, what was seen is that these space-times have very different expected chaotic properties than ADS. For instance, the out-of-time order correlation function have an oscillatory behavior rather than being exponential. So we have this kind of expectation of a very different chaotic behavior, and this maybe can guide us how to look for a dual theory to these space-times. All right. So how do we proceed in looking for duals of these interpolating geometries? So we know that these are infrared modifications of anti-de Sitter. And therefore, we expect that we may need to consider relevant deformations of the SYK model that would influence in the infrared. And for most of my talk, I'm going to consider infrared modifications that are dual to interpolating geometry not between anti-de Sitter and de Sitter, but between two different types of ADS, because these are better understood and they will help us develop the tools that maybe then can be used for interpolating geometries between de Sitter and ADS. And I'll come back in the outlook to tell you what exactly I think needs to be done to proceed. All right, so then the goal of this talk will be to study the chaotic properties of SYK RG flows. The dual is indeed quite well understood in this case, so it's known which exactly interpolating geometry that thing should be dual to. Yeah, and as I said, I'll come back to the Sitter towards the end. All right, so here's the outline after this like rather longish introduction. That's the outline of the rest of my talk. I'm going to give you a little bit of background about the SYK model and its relevant deformations. I'll talk about possible signatures of chaos, and perhaps I'll have some addition to make to this literature about signatures of chaos. And finally, I'll go back to the Sitter in the outlook. All right, so the SYK model. The SYK model is a model built from n Majorana fermions, which satisfy the following anti-commutation relation. And the Hamiltonian of the theory is a sum of Q-body interactions. So that means that in every term in the Hamiltonian, Q of these fermions are talking. But it has something special in that it has random couplings sampled from a Gaussian distribution with zero mean and a certain variance given by this coupling constant J. This model is generally chaotic. However, for the special case of Q equals to 2, it's integrable, and we will talk about that. You should care about this model, not only because of holography. In the condensed matter literature, it's a very well-known model because it's used to model strange metallic behavior. So a few things I can tell you about the SYK model. So the partition function of the SYK model can be written in terms of a self-energy and the fermion bilinear, which is essentially the fermion two-point function. And what's nice about this model is that when one starts taking limit, then the model becomes tractable and one can solve many things. It's quite a special instance of a model that is chaotic and strongly interacting, but nevertheless, one can compute things. So if one takes the large M limit, then it's possible to do a saddle point approximation, which is given by the solution to this Schwinger-Dyson equation, set of integral differential equations. And then if further then one takes a limit of large Q, so many fermions in each interaction terms, these equations become ordinary differential equations and the solution is analytic. So you can see kind of a difficulty chart of this model. I will focus only on large N in this talk, or large N and large Q. Some more properties. So one of the things that make the SYK famous is that at low temperatures it behaves like a conformal field theory. It also drove the connection to holography. So at low temperatures or high inverse temperatures, the theory has a conformal behavior with an anomalous dimension for the fermions of 1 over Q. And of course, the two-point function behaves accordingly. It's maximally chaotic. So that means it saturates the chaos bound. And it's dual to nearly anti-de Sitter 2 solutions of JT gravity. Right, and so that makes us think that infrared deformations of SYK could teach us about interpolating geometries between ADS and whatever in the infrared. So let's talk a little bit about deformations, how it can be deformed. So as I said, I expect that the deformations are, that the relevant deformations will correspond to modifications of the gravity deep in the bulk. And it's not that easy to build relevant deformations of SYK. I can explain if someone asks. But if one considers disordered operator, like the Hamiltonian itself, so essentially we take an SYK Hamiltonian deformed by another SYK Hamiltonian, then this deformation would be relevant as long as the number of fermions in the second Hamiltonian is lower than the number of fermions in the original Hamiltonian. This case is solvable, so all the techniques that I said that existed at large N and large Q can be generalized to this case. And further, the dual, as I said, is well understood, at least at the level of thermodynamics, the Ortok, and so on. Well, now the Ortok. Right. So the dual is essentially an ADS deformation of a larger ADS spacetime. So what do I expect from the behavior of these models along RG flows? So essentially, I expect that the behavior will depend on the temperature. So I expect that when the temperature is very, very high, I'm in the UV, the theory is practically free. When I'm in some intermediate range of temperatures between J and S squared J, S is the parameter that controls the relative strength of these two Hamiltonians. So in the intermediate range, I expect to see a behavior that doesn't know about the relevant deformation. So it only depends on the original SYK Hamiltonian. And then if I go very deep in the infrared, so very, very low temperatures, I expect a behavior that will depend both on the original Hamiltonian and the relevant deformation. And so this leads us to expect both regimes are strongly coupling, and we expect that both of them are nearly maximally chaotic. But it's a question of whether we can analyze this near maximal chaos using the standard tools that people typically use to diagnose chaos. All right, so a few slides about quantum chaos and how to recognize that. So there are a few different signatures that people use to diagnose chaos. First of these is the Lyapunov exponent. So that's the idea to compute the out-of-time order correlation function. And if the system is chaotic, the out-of-time order correlation function behaves exponentially with a characteristic exponent called the Lyapunov exponent. This exponent is bounded, famously, by 2 pi over beta. That means that the chaotic spreading cannot be in any physical system faster than that speed. In order to define the out-of-time order correlation, we need a separation between the dissipation and the scrambling time. Otherwise, there is no regime where to watch this exponent dominating the behavior. And that happens at large n. So that's what I'm focusing on today. But you should know that when we are at finite n, this probe is useless. And that led people to propose this idea of Krylov complexity. And I think we've heard quite a bit from Pavel, but I'm just saying in a few words, this Krylov complexity is a measure, an alternative measure for chaos that essentially measures operator spreading under Hamiltonian evolution. So what one essentially does is build an orthonormal base coming from orthonormalizing and the operator and the different commutators of the operator with the Hamiltonian. And what this Krylov complexity answers is how many such operators are needed to expand the time-evolved operator. The average number of such operators that are needed is this Krylov complexity. It also behaves exponentially in chaotic systems, to some kind of spreading epidemic mechanism, with a characteristic exponent known as the Krylov exponent. That would work at finite n. It's much, much, much simpler to compute than the Lyapunov exponent, so people tend to go there. It's a bit of a debated signature. I will add to this debate towards the end. But it's a much easier signature to compute. You can compute it from the two-point function, and so people like it a lot in the quant literature. All right, there are bounds on this Krylov exponent as well. Presumably, it's also bounded by the bound on maximal chaos, and also it was proven that it bounds the Lyapunov exponent from above. However, a statement that you can find in all this literature is that this bound should be tight, which means that we can do a much simpler calculation rather than calculating the OTOC. And then we will get kind of the same result, something that was tested for large Q. So I would say that we did test that, and anywhere except SYK at large Q doesn't work. So these two exponents are absolutely not the same, and only one of them can diagnose chaos. So here I'm showing you just the next order in a 1 over Q expansion. You can already see that there is a small deviation between the two exponents. All right, so let me just pause for a second to tell you how much. So I'm going to show you a bunch of plots that we did, both of the Lyapunov and the Krylov exponents in these flow geometries. I'm just pausing for a second to let you know that there is tons of numerical work hidden behind these plots. So a lot of numerical difficulties associated in particular with low temperature regimes. One has to solve the Schwinger-Dyson equation using an iterative procedure in Fourier space to get the 2-point function, and then this 2-point function gives you the Krylov exponent. And then for the 4-point function, you further have to diagonalize a certain kernel that goes into the definition of the out-of-time ordered correlators. But in short, these are mostly many sleepless nights of coding by our students and postdocs. All right, so a few plots. Just to test the tools, this is the case of the single SYK model, but with finite Q, so not large Q. And what you see in the plot, so in blue, you see the Krylov exponent. In the dots, the round dots, you see the Krylov exponents. And in the dashed lines, you see the Lyapunov exponents. They look in this plot as if they match. There is a small difference between them, but this difference is very small. So it's actually still quite a good approximation to say that they are the same. And you see how the theory goes from, let's say, the high temperature regime on the left, where it's nearly free, to the maximally chaotic regime on the right at low temperatures. This plot is normalized in such a way that maximal chaos is 1. That's on the y-axis. And so you see that this transition from a free theory to a maximally chaotic. Yeah, all right, but that's kind of the trivial example. But let's go to the flows. So in the flows, we can start by studying the simplest example. So essentially, I take 2 Hamiltonians, but the large Q limit, I told you that the large Q limit was much simpler. So I take a Hamiltonian with many fermions, Q, in each interaction term, and I deform it by a fermion by half that number. It's still infinity in each interaction term. So that model is solvable, at least the 2-point function is solvable analytically. And so you can look at these signatures of chaos in this model, and that's what you see on the plot on the right. So as a function of temperature. Let's start by looking at the Lyapunov exponent. That's the dashed black line. And what you see essentially is that we start on the left at very high temperatures with a, let's say free theory, go up all the way to a maximal chaotic regime, and then delve back down. So we have some region where the theory is strongly interacting large N, but it's not maximally chaotic. And then go back up to the second deep infrared regime where it's chaotic again. So this is already kind of a non-standard, interesting behavior that we are not used to seeing in large N strongly interacting theories. And you see that indeed this Lyapunov exponent is able to diagnose the transition between the two chaos regimes in this RG flow. The Krylov, on the other hand, so you have on the top 2 methods to compute it. The blue dots, essentially, as you take more and more terms, converge to the orange curve. And as you see, it doesn't see basically anything. So it doesn't see chaos. It doesn't see the transition between the two chaotic regimes. Basically monotonic all the way. All right. And I didn't show, but you can also study the dependence of this dip of the Lyapunov exponent as a function of S, like so this region where there is not maximal chaos, the transition between the intermediate infrared and the deep infrared, and that goes like 1 over S squared. All right. Now let's go to a different kind of flow that has a much more special behavior. This will be a flow from a chaotic to an integrable system. You remember that I told you that Q equals to 2? Oh, really? Oh, okay. But that's fine. I will finish on time. Don't worry. So that's a flow from a chaotic Hamiltonian with 6 fermions in each interaction term to an integrable Hamiltonian with 2 fermions in each interaction term. And what you see is that along the RG flow, we go from a free theory to a somewhat chaotic theory and then back down to an integrable theory controlled by this H2, which was just 2 fermions in each interaction term. It's like a mass fermion Hamiltonian. And again, the Lyapunov exponent sees this transition, while the Krylov exponent is unable to diagnose it. It's monotonic like before. There's only one case where we did not see that. This case deserves future exploration, but I'm going to give you a glimpse. You remember that we had Q equals to infinity was rather easy to solve. You can also take Q equals to infinity and deform it by an integrable deformation. And in this case, you see something special. You see that it seems, at least, but this is somewhat, we didn't explore this all the way through, that at a given fixed value of the temperature, the theory goes from free to somewhat chaotic and back, but it seems that at a given point in temperature, the theory becomes exactly integrable. So the Lyapunov exponent, we are unable to distinguish it from 0. And in this point, the Krylov complexity stops behaving exponentially. So that's this nonsensical point that you see on the top plots. And so there is a question if there is really a strict phase transition back to integrability in these models. But in any event, in all the cases that we were actually able to define a Krylov exponent, so that the Krylov complexity was spreading exponentially, we saw that it was always monotonic. All right, so here I am at the end of my talk. So that's the short take-home message. So Krylov, bad, Lyapunov, good for diagnosing chaos along RG flows. I should also say that there has been some literature. There has been a paper by Julian Sohner and Eliezer Rabinovich and friends that claims that this Krylov complexity is dual to the volume or the length of geodesics in ADS2. This was for a very specific setup, not the one that I'm studying here. But I should say that we did study at some point the volume in these interpolating geometries, and we saw that also the volume, just like Krylov complexity, does not seem to see the flow. So that goes in line with at least being consistent between the relation of the two. All right, many questions. Is the Krylov exponent always monotonic in cases where it can be defined and when the system is Hermitian? That's what we saw in all our examples. What can you do? Can you do anything at finite n? There are many questions. But I want to look back to the sitter because I told you that this was all related to the sitter, and so far I've been studying flows, interpolating, like the dual of interpolating geometry between two ADS spacetimes. But we saw various non-standard chaotic behaviors in these flows, and we know that the sitter space has non-standard chaotic behaviors. So we would like to understand which type of RG flow could lead to a de Sitter interior. This, of course, will be very different from the things that I've been telling you, but there is reason to think that the relevant deformation that I need to add to SYK to make at the Sitter interior would have to do with the study of open quantum systems. And there are several reasons to think that, so let me give you a few. Why would the Sitter be dual to an open quantum system? Well, for once, there is an open boundary at future infinity where energy can leak from the static patch. There's this Gauss-Wald theorem that tells us that perturbations essentially send the cosmological horizon away, so it makes contact with the larger part of the system, opens the wormhole, has all sorts of names. And that's kind of what we expect from an open quantum system, is that we can, if we do some perturbation, maybe we are able to see an additional part of the system. And finally, this I didn't tell you too much, but you can study the thermodynamic behavior of the gravitational interpolating geometry, and you would find an exact match to the thermodynamic behavior of these deformed SYK models. But if you do an analytic continuation and you send the parameter S to I times S, you will then find a match to the thermodynamic behavior of the interpolating geometry with the de Sitter interior. So it's not clear at all what this means, a Hamiltonian with this I inside, some non-Hermitian Hamiltonian, but sometimes there are this type of non-Hermitian contribution involved with open quantum systems, so these all are hints towards the fact that we need to consider open quantum systems in this context. Yeah, many people studied signatures of chaos in open quantum systems, both the Ortok and the Krylov, and so now we are trying to explore connections between these ideas and the interpolating geometry with the de Sitter interior. So yeah, that's it. Thank you very much.
Thank you, Shira. Great talk. Are there questions? Yeah.
Hi. I would like to just make a brief comment. So in general, I think I've been trying to say also that early time measures of quantum chaos are maybe not the best measures of quantum chaos, so Lyapunov included. So in particular, it's known that there are systems which have even maximal Lyapunov behavior and are not chaotic. So I would like to push, and I think with Adrian and so on, we have advocated this, that you should look at spectral measures of chaos, also in the context of Krylov. Maybe then you can have a new slide that says Lyapunov bad and Krylov bad, but you know, I am still waiting to hear about that.
I see. Next year, update to the slide.
Other questions? Yes, please. Here in front and over there.
Thank you, Shira. In that plot that you have the Lyapunov going like, no, I think it's before, going like to 1 and then taking the bump, right? Going down.
Yes.
So holographically, what part of the space that bump corresponds to, if you were to say?
Yeah, so those that I showed you had kind of abrupt gluing of de Sitter to ADS or ADS to ADS. But there are many versions. Essentially, if you play with the dilaton potential, you can get kind of smooth transitions between ADS and ADS or DS and ADS. And this bump is essentially corresponding to this transition region.
This smooth transition.
Yes.
Right? If you were to put the wall with matter, what would you have there?
I don't know, because I have much less freedom in choosing. I mean, I do an SYK deformation, and I can do much more control of the bulk to get many things that are probably, I wouldn't know how to implement them as a flow of SYK theories. Maybe, I mean, in principle, you could maybe start piling up different deformations, and maybe there is an exact match between the different dilaton potentials and, SYKs with many, many added deformations, but I wouldn't know to tell you how to do an abrupt transition or even take a limit.
Thank you.
There was a question there and then in front. Okay. Any order is fine.
Yeah, okay. So just to point out, in this works with Julian and friends, we didn't study RG flows, but we study situations in which there is some transition between chaotic and integrable regimes. And in that case, we did show that Krylov complexity is sensitive to these transitions, but the features of it that are sensitive to them are features that appear at timescales that are later than scrambling time.
Oh, I see.
And I think if one studies the Krylov exponent, one is focusing at pre-scrambling timescales, so being blind to these other features in principle.
I mean, if you, yeah, there are also things like if you look at some of the Langsos coefficients and you start to massage them, even like early Langsos coefficients, but a specific piece of data that is not exactly, say, the slope when it starts being stable, then you do see something. Just maybe I wouldn't call it Krylov complexity, but maybe there is some data in the two-point function that you can extract. At the end of the day, in SYK, everything comes from the two-point function. Even like to solve the auto, you are diagonalizing some kernel that you are building from two-point functions, and there are analytic continuation. So at the end, I mean, it's a kind of a special model, right? Maybe there is something that can be, yeah. But maybe not under the standard definition of the Krylov exponent.
We were looking at things like the saturation value of complexity, which is something that appears at exponentially late times. So a way different time scale, for instance.
Yeah, but we can talk. We can talk some more.
There was a last question there.
So, so both in weakly coupled systems and in SYK or holographic systems, Lyapunov exponent is special because it also is correlated with the long-time hydrodynamic behavior. Is there something in the Krylov complexity as well that has some imprint in actual sort of long-time observables that you may know? Or
Can you re-say the question again?
So famously, the Lyapunov exponent in SYK models shows up in analytically continued hydrodynamic response functions as a pole skipping point. There's been a lot of stories. And that's the exact Lyapunov exponent. So the question is, does the Krylov exponent show up in any other observable?
Yeah. Well, in some cases, you can read it from the first divergence in Euclidean time of the Euclidean correlation function.
Oh, okay.
So when you don't have, I don't know, staggering of the Langsos coefficients and things like that. I mean, in specific cases that are mostly those relevant here, you can read it from the pole of the two-point function.
Okay, thank you.
Okay, I think it's time to stop. So let's thank Shira again.